In this video, we'll dive deeper into tilings in hyperbolic 3 space, while touching base on other related concepts such as platonic solids and wallpaper groups. Now that we have the basic understanding of what we'll discuss in this video, let's go ahead with a few definitions.
In Euclidean space, we have both regular tilings, which consist of a tile being a regular n-gon with a fixed n, and semi-regular tilings, with each tile being a regular n-gon while each vertex is identical. For example, right here we have an example of a regular tiling. Here you can see each tile is a hexagon, which is a regular n-gon, and that goes to show that each n-gon tiling in this figure has a fixed n, and hence it is regular. While, for example, for this image here, we have a semi-regular tiling. And here, as you can see, each vertex has 3 triangles and 2 squares, which goes to show that each vertex is identical. And of course, a triangle and a square are regular n-gons.
Taking a further look at semi-regular tilings, let's see another detailed example of semi-regular tilings in which we have 5 tiles at a vertex. The following formula helps us figure out how many which regular n-gons are missing in the tiling. For example, if we have 4 triangles at each vertex, then there is 360 minus 60 times 4, which equals to 120 degrees remaining, and hence by using the formula, we now know that there's n is equal to 6, which means that our 5th tile is a hexagon.
Now, on a complex plane, let's imagine a sphere-like model, which has its uppermost point as the North Pole. Let's take a look at this image. So this would be the complex plane with the sphere, and the uppermost point is its North Pole. This resembles a Riemann sphere, and you can refer to the abstract to see how each point on the complex plane gets mapped onto the Riemann sphere.
Have you heard of platonic solids?
No, I haven't. What are those?
Let me explain. There are 5 platonic solids, and a unique property about them is that all of its faces are identical regular polygons, and there are the same number of faces at each vertex. Platonic solids are also known as regular polyhedra in the case when it's a convex.
Oh, great. That's amazing. They're so beautiful. There are infinitely many regular tilings in hyperbolic space, which can be viewed from many different models, such as the Poincare disk model and the upper half plane model. However, before we give you a few examples, let's look at a few definitions.
A regular polygon is a polygon with all edges having the same length and each angle having the same measure. One of the types of tiling is called dual tiling, which is created by joining the centers of each tile. For instance, we take a look at having a regular tiling with 6 squares at a vertex. This image will make the picture look more clear to you. In this image, we have a square in the Poincare disk model, and we've reflected that square multiple times so that the image is created. The same tiling looks like this in the upper half plane model. Pretty cool, but it takes a while to create. In the upper half-plane model, lines are considered to be semicircles with the center at the x-axis and vertical lines. In hyperbolic 3 space, lines are defined similarly with the condition that it intersects at a point with each plane. In this image, these are the lines that intersect with the xy plane when z is greater than or equal to 0.
Take a look at an application of tilings, known as the wallpaper groups. But before we do that, here is an important definition to keep in mind: a tessellation. A tessellation is an arrangement of shapes closely fitted together, especially polygons, and these shapes do not overlap or have gaps in between. A wallpaper group is a group of identical symmetries on a plane which consists of a translation, rotation, reflection, and glide reflections. These patterns are usually repetitive and are in a group of isometries. There are exactly 17 different patterns, individual wallpaper groups, and the reason why there's only 17 is because there's 17 different tessellations which make up a wallpaper group, and also because there are only exactly 17 different symmetry groups in mathematics. Indeed, each of these wallpaper groups are beautiful, each in their own way.
We hope that you enjoyed learning the different tilings and their applications in Euclidean and hyperbolic space, and that the next time you see a wallpaper design, you'll be able to think back to wallpaper groups.
Thank you.